everyone, and welcome to our webinar today. We're going to be going into some advanced Adams car techniques for modeling for formula. We have two speakers today talking about a couple of different topics. Our first speaker, Alexis Del Rio, will be speaking on template building, which is important if you want to change the topology of your model. Alexis joined Hexagon in 2018, and I think that was right after our part of the company had joined Hexagon. And he's based in Cobham, London, in the UK, where he mainly works with Adams and virtual test drive. He is the main technical support person for the Proving Ground encryption toolkit worldwide. And I think this is fun. He is a keen motorcycle rider, and he's very interested in getting our software used in two-wheeled vehicles. Our second speaker, coming up later, will be talking about tire data fitting. Our speaker is Anirudh. He goes by Ani Matanage. He joined Hexagon also in 2018 and is based in our Novi office near Detroit. And he's part of our consulting car services team for system dynamics, and he helps customers with modeling, methods development. He'll make custom GUIs, that kind of thing, helping them use advanced features of Adams Car and Adams View. And he was a student at the University of Texas, Arlington. He was on the Formula team. He was the suspension lead for the 2018 team. And he told me that he started to use Adams Car then, and his advisor was very impressed with how accurately he was able to predict the angles that you would get once they realized the suspension, once they built the suspension. So I think that's, he's somebody who just has a lot of on-the-ground practical knowledge of use of Adams Car. We've got a couple of these main topics today, with this being our third Adams Car webinar. For our Q&A time, that's really going to be open time for you to ask whatever questions you would have about Adams Car. And I think both of our speakers are very knowledgeable and would be very helpful for you. Okay, Alexis, I'm looking forward to hearing from you now on Template Builder.
Hello, my name is Alexis. So today I'm going to speak to you on a variety of topics. So basically, we're going to have a workshop on converting a pushrod to pull rod, but also I'm going to talk to you about some interesting features and some potential issues that you will run into once you try with testing and trying with Adams Car. And at the end, I will give some time to my colleague Anirudh, who will be talking on tire fitting. But before we join that, I want to clarify something that happened one of the questions that wasn't answered last week. I wasn't in the call, so I apologize. And the question was related to OpenCRG and OpenDrive support. So Adams provides support to OpenCRG. And if you look into a model, for example, if I open the typical assembly, which will be the MD9 demo vehicle, and we tested thoroughly things with this. Then once I select my model and I go into any full vehicle analysis, I can try this one. There will be a placeholder for the road, and then I can search here into the shared database, and I can look into all the roads there are. There's not that many CRG files, but you have a few things here. And basically, you will have the option of clicking them. But then there is also this thing called reposition. So let's try first to load this. And then I can click on this Route 66. And then the road will load up. So the first thing you will see is, apart from the fact that the vehicle is at the end of the road, if I click on center and then I rotate, the vehicle is on the air. So once you put it in the right position and rotate it, you will notice that the vehicle is in the air. If you try to run this event like this, it will fail because the vehicle will try to land on the road. It will not have enough iterations to finish, and it will fail. So then there is this reposition file. It may not be. Now you are at a position in which the vehicle is through. So the tires need to get through by a few centimeters. It's green because it's just out of the limit of the road, but that's not a problem. So the road is extended beyond it, and then you will have that option. But remember, the tires need to protrude through the road. Otherwise, you're going to have equilibrium issues. And this is something I will cover at the very end briefly. Then the next question was if we provide Open Drive support. No, we don't. That's more for road networks and nice visualization of roads. That's not the point of add-ons. So OpenCRG, yes. OpenDrive, no. And OpenCRG is also covered in the documentation. Then message window. Before we do the template, you will notice when you run Adams for the first time and you load the model, they're going to have this message window. And that message window will be here. Please don't click on clear and close. You want to understand what's going on behind the bar, the curtains with it. So I call the MDI demo vehicle for this in this case, and then it opens all the different parts, all the different subsystems, and it's calling all the property files and doing things in the background. Then it gives me all these input communicators that are not connected, and it gives me them as a warning. It's not an error, it's a warning. And there's very interesting things here. For example, in this vehicle, it's telling me that my anti-roll bars connection are connected to ground. If your vehicle has anti-roll bars, and in this case, it doesn't, because if I check here, you will see that there are no anti-roll bars, you are likely to have some issues with it. It could be that the anti-roll bar stays fixed in the ground and the vehicle moves forward, but it could be that the simulation fails. So if you have anti-roll bars on and these messages happen, you may want to check what's going on with your model. There is likely an issue with it. So never close it, never clear it, always try to understand. Then we said we were going to show you how to create or how to convert the actual pushrod suspension into pull rod. And that's a fairly straightforward job. So in this case, we're going to go into template mode. Then we're going to open our model. We're going to go into the formulas. This time, we're going to go into the formula student, and I'm going to open this one. You will notice that I already did it, but we're going to open this one. So again, read the message, try to understand it. So in this case, the model is from 21, Adams release 21, and it's converted to 24. And there's a few adjustments, so just make sure that there's all of them right. And potentially there could be errors, although it's not normally the case. So then what we want to do is right click and say, for example, front. I want to familiarize myself with it. Then I want to check, maybe I want to do it in wireframe. Maybe I want to do it, see the icons. Then maybe I want to rotate. Maybe I want to go back into solid. I can also do it with the keys. So because there's a small key there. So you can also do that with the keyboard. Then you want to see, for the first thing, if your model is right. You want to make sure that your model, when you start, is 100% correct. So right-click at this information button and click on the V. This will do the Google count for you. And specifically, it will tell you what has no mass, and especially what is redundant or not, and if your model is over-constrained or not. Once you have checked this, you may want to see how the model is associated, because we need to change the actuator from the lower control arm to the upper control arm. There's a variety of things here, so you can do right-click into the part and then click associativity. And this will open a database navigator, and it will tell me in text what is connected to and what is using to make sure that this component exists by just clicking on these two buttons here. You can also do it through here. You will have the same options. To get into this menu, there's different alternatives. Tools, database navigator, and then you can check associativity. There's many other options there, but the most important one is you may want to see the graphical topology. So in this case, we right click, associativity, then we click here and do graphical topology. In this graphical topology, it's telling me that this component, which I can also interrogate, and all the components you can also interrogate, you can click on modify and you can check how it's been made. So it's using a couple of hard points and it's using some coordinates to exist. Then you also have a couple of joints, and then you can, to be sure, you can select them and it will highlight them for you. And the same thing at the top. So what we want to see is this one is connecting the actuator against the lower control arm. That's not right for our pull rod. So we need to make sure that this is changed. So we want to modify this and we want to replace this, which is, again, I selected and it's the lower control arm. So I want to make sure this is different. So I can type if I know the name. I can pick from the screen. I can guess, or I can browse. Browsing will again open the database navigator in a different way. So the best thing in this case is I pick and then I do right click to make sure, in case there's many things in the screen, you can select the one you're interested in. So now it changes to upper control arm. And when we go again into the graphical topology, still the lower control arm, and then the upper control arm. So now it's done. So now you got it connected to the right thing, except that the position is not really the best one. So then what you want to do is to change the hard points. You want to investigate what hard point they are related. And when you build templates, you start from top to bottom. You will start doing hard points construction frames, which are basically markers connected to ground. Then the parts, geometries, attachments, and so on, until you finish with your model. In this case, we want to see, we want to either modify individually or we want to do it through the table. So I can always click on the table, then expand it, or I can right click here and say my upper control arm, or here and select the hard point I want and click on modify. So I got a bit of a check list here, tells me that the main one is this product outboard. So I can say the outboard will be, it's this one. So we can always test it. Yeah, it's going up. So 283, that will be for set. Then 59 minus 594.1 minus 512. Yeah, so we click on the screen, rotate. That seems more likely. But then I have to move all the rest of the suspension. Then I can go again, selecting them individually. I can go here and then click on each different one. That's completely up to you. But I got a different method, which is maybe a bit faster, depending what you're doing. So you can always say command window, a point, and then I click tab, modify point, name, and then I need to select one of these. And then when I click enter, it will move it. So you've done it through the command line. Another option, which will be much better in this case because I have a few things, is if I click F2, I have this hard point change in which I basically add them all together. So I'm basically calling a script instead of doing them individually. Boom, it makes it for me. So now I'm in a position in which I could start testing. It doesn't look amazing, but at least you got the right ballpark figure. So then I save it. You can save it as a binary or as an ASCII. It's up to you. You want to be sure you save it in the right database, because I want to continue using it. and I don't want to be looking into different databases. And then I go into the standard interface. I create a new subsystem, in which this case is going to be front. Then I search run database. Then I search for the right model. And we did it Pushrod. I call it Pushrod. Okay. Let's use the right one, the Pushrod I did the other day. Then I gave it Pushrod. So now I have my subsystem, and then I create a suspension assembly. And I want to create a suspension assembly because I need to make sure that my model is correct. So I can search for it here in the database. But if I click here, it already recognized that it's loading in the session. So I can do this name. And it's going to be attached to the suspension test rig, which is the right one. I don't want to add any steering. I don't want to add anything else or any anti-roll bars. I want to be sure that the model works first. So click OK. I read that everything makes sense. And OK, I have no subframe. I'm happy with that. My uprod is connected to ground. Makes sense. They're going to be connected to ground inside. And so on. There is no steering. So that makes sense. And then I want to run a simulation. I want to start by a parallel wheel travel. But before I do this, I want to compare. And the basic comparison will be against the default model in the database. So we can do from suspension. I load it up. It should give me a reason of the same type of not connected inputs. In this case, I got more things going on. So I want to set up my assembly in such a way that replicates the other. So I got this toggle subsystem activity. I remove the steering and remove the anti-roll bar, because I want to be sure that what I'm testing is the right thing. So we're going to start with the suspension test, which is the pull rod. We're going to say, for example, 150 minus 50, and then click apply. This should run my simulation. And then I change the model and rerun it. And then the plan, instead of playing videos, is to replicate what's going on. So I can do, for example, select them both with Shift, and then I can say review, general report, and it will create me the reports for each one. So I can compare what's the difference, and if my results make sense according to the data that I already have. Or I can go in generate plot, create new plots, and this will create me the typical plots I need for this type of length. And then I can review each page to see how far I am. For some reason, my screen is getting black. Okay, so and then you can see what are the typical matrix that you want to see. And that's everything for this. So we're gonna go back into my presentation, and then I'm gonna introduce you the database navigator, which is what we touched before. So this is the menu that allows you to browse your model, and you can interrogate it. You can check the graphical topology. You can see things in different way, and you can interrogate it the same way as you will do with right click in the Adams model. The next thing is the bottom right toolbar. This is a very useful toolbar that you have. So this one shows you the database that you're currently in. There are different methods to change it, but the main one will be saying, I want to work in 21. So my model will be saved there. Then this will allow you to deselect all. This button is the one I showed you briefly, is the event browser. So when I close this, I click here, and then all the events that you've been creating during the day, they will be saved here. This one allows you to switch in variants. It may not be relevant to Formula Student, but if you have a family of vehicle models in which you have subframes or not subframes, semi-rigid or fully rigid subframes against the body, or front-wheel drive, rear-wheel drive, you will be able to create variants in the same assembly. This is a communicator map, which is quite interesting if you have a full vehicle. It will be a bit too far on what you are interested on, but will allow you to see how things are talking. Because when Adams builds a model, he will need to check that how they communicate between each other to make sure that not only they are placed in the right position, but they are also connected and working in the way that is expected to work. You can also click on each line and it will tell you what they are. So if you eventually want to go further into creating your own templates, you may want to benefit from it. This one opens the command navigator, which is a different menu. Basically, 99% of the buttons that you have in Adams, they will be here. So you can select them and create them through that menu too. This will stop the simulation while running if possible. So be patient with it sometimes. And assures you if you press right click on the information, you have 4 options. So this one will open the database navigator. This one will give you a list of model topology by connections. This one will do it by parts. And this one will verify the model. So the most important one is that you verify your model very often. Make sure that it's not over constrained. That will kill your simulation and will give you lots of headaches. Then simulation files, the typical files you're going to have in another simulation. You will start with your database, and as soon as you click apply or OK in your event, so if I say modify and then I want to click on apply, Adams will create, depending on the options, Adams will create a solver file, which is the ADM. That's basically a single file with your whole model. An ACF, which is the simulation script. So what is going to happen? It's going to run equilibrium, it's going to run a certain event, accelerate, brake, and so on. A log file with certain information of the vehicle setup, how you set it up, so that's also important. An XML, which is the event builder file, and an SDL, which is the Adams driver information. So you can also interrogate your model if you go into the event browser. Then you have the option of checking the models that I did, or maybe I want to do something acceleration and I want to see what's going on. So any event that you run in Adams, you can open this in this event builder. The top part will show you how the vehicle is controlled, and the bottom part will show you what's happening through the controls into the vehicle. So how my steering is controlled, how the throttle, brake, gear, any conditions that I have to stop the simulation, and so on, because I can also add others and modify the existing ones. And the ones at the top will have the PIDs for the vehicles, the trajectory planning, and so on. Then once the simulation is finished, if it runs successfully, you will have the results file, which will contain everything. The request, which will be any request that you specifically created or the model has. In this case, you can have for the suspension, if I double click on it, then I have these outputs, request, and I have this toe and camber. So this is specifically made, and you can make them up if you want. Then the graphics and the message file, which will contain the simulation log file. So the message file will be living in your working directory, and it will look like this. And it's important that you understand it to make sure that your simulation runs and it doesn't fail throughout the simulation. If you happen to have problems with your simulations and the model doesn't run, our first question will be, can I have the message file? Because that will give us a hint of what's going on. And then equilibrium. Equilibrium is basically putting the vehicle on the floor and make sure that it balances out. So it's very important that you can have this right. Once you start modifying your model, please don't change all the hard points in one go, please don't change all the bushings in one go and attempt to run the simulation. Do things in steps, bit by bit, step by step, and make sure that everything works. To find information, you have certain solvers, the setting solver, they are here. And then you have one of them will be dedicated to equilibrium. You can click on more, but with these three, you should have the majority of the things sorted. I also give you a few examples. Best thing is that you can search in Sync Companion for equilibrium or search for these two articles. They will give you a hint and a good explanation on how the simulation is on how to solve out the problem. This will be the typical issue. You will have a certain complaint from Adams telling you that there is an error, and there's going to be certain deltas. This number normally being very large means there's something very badly made, and it gives you a hint of what it could be the problem. So in this case, it may be related to the tire. And also in the web browser, you will have a red dot telling you that your simulation failed. So playing with these buttons here, especially you may want to increase this, but don't go over the roof. If you do like this, and you still get issues with equilibrium, it's too far. Don't go over 400. That's a general advice. You may want to relax this. If you stop the mouse, it will give you a hint of what each one does, and then you can interpret it. If you click F1, the help will come up, and then you can see what's going on and how you can try to understand each button. And then this is my bit, and now I will leave my colleague Annie to do the tie fitting talking. Thank you very much.
Thanks, Alexi. So the last slide that you saw on Alexi's presentation is the location of where all the tire data fitting like example files are. So that's where you can get the standard files and then work with them to to build your own tire model. So on the left, you see the car that I was part of. This was what we designed in 2018. And I have the suspension. So first, I'd like to show you guys what we did slightly different from everybody else for our model back in 2018. And is also, I'd like to show you guys like the other capabilities or the other things that you can do with an Adams car model. Here, in traditional FSAE cars, you hard mount the wings to the body. In our case, we connected them slightly differently to the suspension, and here's how that works. So I've done two sets of analysis. One is the parallel wheel travel and the roll analysis. The reason I've already done it beforehand is so that I save some time and show you guys the important stuff and not the boring things. So here's what the parallel wheel travel looks like. I'll show you guys the left view so that you understand how this mechanism works. So let's see. So as you can see, the wing goes up and down with the wheel. So that way it like moves with the wheel. And to create this, as you can see, there's a lot of extra stuff that I've built here in the template. I can show you guys the template a little bit. Yeah, so this is the custom template that I built for our special mounting system for the wing. As you can see, there's a lot of different parts, a lot of connections, and all of this can be done within Adams too. And you can do this too. It just takes a little bit of time and effort. You can analyze any kind of special mechanism that you decide to put on your model, or if you want to test it and check if it's feasible, if it's possible to do this. For example, for me, it took about 2 to 3 weeks for it to even come to a point where it was actually working even half as much as I wanted to, like how I wanted to perform. And the other thing is how it works in roll. So we wanted two things, not just like for it to sync with the tires, but we also wanted decent performance in parallel wheel, as in bump and also roll, since most of the time the car is rolling in terms of how it travels around the track. So as you can see, it again, same thing happens. It rolls with the suspension. And the main advantage that we get actually is the same. And For the rear, we had a very similar thing. We are again connected to the suspension here with a bunch of ball joints and all of those things. Of course, the constraints that you're using has to be in line with what you plan to do actually in the suspension. So make sure that the joints that you're using, or maybe you need to use bushings instead of joints. So make sure that you make the right decisions there. And then as you can see now, in this case, our wing just slides from one side to the other, so it maintains that angle of attack, and that doesn't change. So I'm sure the aero guy was very happy with that. And similarly, in parallel wheel travel, it just basically just goes up without changing any angle for the wing. So it just stays there. And the bigger advantage of this was actually at the full vehicle level. And here I've done 2 simulations. One is the braking simulation, and the other one is a normal skid pad simulation. So I'm braking at about, the peak braking is about 2 Gs here. And let's see what happens to the car when it does that. So on the left side is the special system. On the right side is the standard one. And look at what happens at about 1.5 seconds. This wing is dead. It's in the ground. It's been like, and every time it breaks, if your car breaks that hard, it's gonna like destroy the wing bit by bit. On the other hand, this wing is still in the air. It's not hit the ground. It's safe, and that was the main objective so that we kept the wing from like hitting the ground every time we brake too hard. And the other advantage that we got from this was, I'm not sure if you guys can see this, but this here, the angle of attack for this wing has changed. It's rolling quite a bit because it rolls with the frame or with the body. On the other hand, this one is much more flat to the ground, so better aero in general. So that's how you kind of get better. You can analyze your linkages or your custom linkage system if you decide to put something on the car, or if you guys decide to do some sort of research to like build a different type of ARB, for example, because there's those blade type ARBs and all of that stuff. So you can do that also. Just have to constrain it correctly and do all the steps. Basically, like Alexei said before, check your model, verify that all the constraints are correct, you're not over constrained or under constrained, and then hopefully everything will work out for you. This was the first part of the presentation, just to show you guys other capabilities of Atoms mainly. And the second part is to do the tire fitting. When you get, so all FSAE teams have access of data from the tire testing consortium. You have to pay a small fee, like a membership fee to them, and you get the tire testing data. What you guys have access to, of course, is the raw testing data, which will look something like this, it is super noisy. So it's not easy to kind of fit this kind of data to get your actual tire. And you can see like this is the lateral force versus the slip angle. This is the aligning moment versus overturning moment versus the slip angle. And this is the aligning moment versus slip angle. Now, this is obviously very noisy, and to draw a line through this is going to be super hard. So what you can do is filter this data, and it's very simple. It took me like a few hours to write it back when I was part of the team. All you do is you can use Python, you can use MATLAB, you can use Octave. All of these softwares have either built-in features, or you can use the existing code and just basically filter your data. And one thing that you can do is just go to Stack Overflow. You'll find 90% of the code there, and you just have to maybe change it a little bit to adjust it to what you need to get out of the filtering. Once you've done it, it looks something like this. Now, if you compare it to what this versus this is completely different. Fitting a curve through these lines is going to be much easier for any kind of tool. And the same happens. This is the lateral force. Here's the overturning moment. Again, pretty smooth lines in general. And the same thing happens for aligning moment. Now, when you have these curves available, you have to create what are called TDX files for which are recognized by the tire data fitting tool in Adams. Once you have that, and each file you can find the files here wherever your Adams is installed. Go there, go to a tire, go to tire data and car. You'll find the sample files there, and use them to basically, now that you have fit the data, you export that information, and then that information goes into into these TDX files. As you can see, you have to obviously put all the dimensions and things of your model here, of the tire here. Then as per these channels listed in this list, you just organize the data in exactly that format, and then you let the tire TDFT do its thing. So of course, and one note, keep your tire data organized by normal load, camber angle, and pressure, so that it's all very, very organized. And if, let's say, one of the curves or something, when you fit the data and you plot it and you see something is weird about parts of the fitting, you can go back and you just edit some of the files. You don't have to edit the whole, or you have to go through the whole set of data to find out where the problem was. That way, it'll just be easier for you guys. And now going to the demo of the thing. Here we go to simulate, we go to component analysis, and we go to the tire data fitting tool. Now, of course, you have to start from scratch, but don't start from an empty file. What you should do is you could go over to the open tire property and add to database option, go to ACAR shared and pick the smallest tire that you can find, which don't pick the MC. MC stands for motorcycle. So here looks like this is pretty much R13 is pretty much the smallest we can find otherwise. So we'll start here. We'll open it. Then you have to click on this one here so that it highlights this tire. Hit the calculator button, which is the tire fitting button, so to speak. I have already pre-organized all the files and everything because I did this fitting back in 2018. So I have all the files available to me. I just go here. I have all my TDX files, all, like I said, all organized according to camber angle, and then after that, according to like normal load and tire pressure. So once I add these files, you'll see that the tire data fitting tool automatically recognizes that these files are basically for they have cornering data in them, and that's because I followed the example from the ACAR shared, the sample files available within the installation. I looked at those files, made sure that my data also looked the same, and then the tire data fitting tool was able to figure out, okay, this is cornering data. Now I go through and basically upload or rather link all the files one by one. One more time. So now I have a look, and it tells me that all of these are pure cornering files, so which means I don't have, I'm not selecting any of the longitudinal files that I have available right now. I just want to show you how it all works, and I actually want to force it to give me an error, which is why I'm doing this. Let's see. So the first thing that you have to do is hit import tire properties. Right now you're on like a default tire property file, so it doesn't have the properties from your tire. And what I want to also show is this window here. What happens when I hit the import tire properties button? You'll see that it says that it adjusted the tire properties according to the TDX files and like adjusted them and got the right numbers from the files, which is why you have to make sure that you put all the right numbers in those in the files. Now, once this is done, it has all the files. All you have to do is say, the data that you have is only force and moments, not any of the extra other stuff. And in general, for FSAE, that's more than enough. And what you do is pick all force and moments, hit the start button, and it'll give you a progress bar here, and you just wait. And it'll also give some messages over here as it progresses through the fitting. Now, in the beginning, I just tried to use the unfiltered data to do the fitting, but I let it I let it stay there for like 3 or 4 hours and nothing happened, as in it wasn't able to fit it. So I had to go and do the filtering part. Otherwise, I wouldn't have. And as you can see, it gave me an error here. It says, I'm not sure if you guys can read it, so I'm going to put it in a pad. So it said that the estimate for QBZ10 is unrealistic and large. You need to set it to 0, fix it, and repeat the fit. So since all the parameters are connected to each other in a tire file and in the back formula, even if one coefficient is messed up, it can mess up all the other coefficients, which is why, and that's why like the tool has a detection feature where it tells you like something seems odd, please go back and check and fix it. So I would go into, I'm going to try to find where QBZ is. Here it is. So QBZ10, as you can see, all the other numbers are pretty small. They're like single double digits, but this one is 245. So that doesn't seem to be quite right. You can also see what each of these parameters is for. So what you want to do is, what it told me to do is set it to 0, fix it, go back, and do the fit again. So my basic point here is don't ignore the warnings in there. Make sure that you listen to them, fix whatever it tells you to fix, and redo the fitting. And now let's see if it gave me another complaint or anything here. Looks like I'm all in the clear for now. So this is my new tire file, which is this thing here. So now that I've done the fitting, I obviously want to know if it was done properly, or if the output is going to be similar at least to the input. So what you can do is say yes to the measurement data option, and we did only cornering data, so we're going to only do lateral slip versus, let's say, let the cornering force. And I'm going to plot it, which is done by this button over here, up here. If I say plot, as you can see, like the green and the blue is pretty decently overlapped, which means you do have a good fit here. We'll check all the other stuff also. We'll check the overturning moment. This also seems to have a decent overlap. Of course, it's not going to be perfect. It's trying to fit multiple different curves and like adjust the coefficients within the tire. It's not going to be like a perfect fit, but it'll be as close as you can get it. And this is pretty decent in general. And let's check also the aligning moment. This is also, as you can see, it's not as great a fit as it was, but we did get the error for the aligning moments, which is why probably like this is not the greatest fit. You can go adjust the QBZ10 and like let it unlock it again, and maybe it'll do a better job next time. So you can work with that. I have already done all that hard work and created a tire. So so once you've done this plotting, you can be kind of sure that, okay, the tire that I have here is at least very similar to the actual testing data that I received from TDC. And then you can run your full vehicle simulation. You can run all of that stuff and get and see how good the answer is, or rather get a good estimate of how your vehicle will perform on the track. For example, like Alex mentioned before, I was able to predict the toe camber settings for the car within an error of 0.15 degrees for front and rear suspension. So I would say that's pretty decent starting point, and it'll save you a lot of time during your testing phase when you're trying to adjust the actual car and get the best performance out of it. And that's pretty much it from my side, and I will leave it up to people for questions and anything else.
Ani, Alexis, thanks for the presentations. I'm going to tell everybody now a little bit about how to access our software and what to expect in the upcoming webinar and how to follow up, that kind of thing. First, to get a copy of Adam's car or any other piece of hexagon simulation software that is listed here, you would need to sign up for the student competition bundle. You could also get a student edition. Those are limited in model size, a certain number of nodes, a certain number of bodies, totally free for any student or professor in the world. And we have different links for that. I'm about to drop both of those sets of links in the chat. The student edition is easier to sign up for. It's just one really simple form. For the student competition, you would need to get other people on your team and your faculty advisor to help you fill out the paperwork. Note that Atoms, but not Atoms Car, is part of the student edition. So I would say if you want to check things out this afternoon, you can install some things soon if you sign up for the student edition. And if you want to really go far, definitely sign up for the student competition bundle. We have one final webinar in the series, and it's on finite element analysis, and also doing generative design, where you would say, here are loads that we want the structure to apply, we want it to be constrained here, and we might make this by additive manufacturing or some other process. You know, computer, go design a part for us. We have software for that. So I'll be one of the presenters for that, as will Joanna Lee Mayer and Lennart Kruger. If you want to follow the overall webinar series, our homepage is at this link here, and recordings are posted on our YouTube page. You can follow me on LinkedIn just for incremental updates on the webinars. Okay, I'm about to drop links in the chat related to all of this, and I'm also eager to hear what questions people have. We have a Q&A feature right here in Teams. So I have a question just to get things started. Ani, you were showing about filtering the data and then doing the fitting within Atoms. And at first I was wondering if your fitting was just, or excuse me, the filtering, what you were calling filtering, was just doing nonlinear fitting, but it seems like you were doing a little bit more than that. Without like reading us the Python code aloud, can you tell us like the general thinking that goes into that kind of filtering? Is it that you're removing outlier points?
So in general, there is just vibrational noise in any testing data. So you saw like basically what I'm trying to do is get the mean of that curve, like so a curve that is passing through the middle of that band, so to speak. So you saw that one curve had an upper section and a lower section, but what the real answer is basically an average sort of that curve. So you want a line or a curve passing through the center of it. So that's what I tried to do.
Okay, cool. Thanks. That's helpful. In the chat, I see somebody has a question. Do we need a separate license to use MF Tire? Now, there's a product called MF Tire that is from Siemens. Ani helpfully answered that question. For Atoms, if you want to fit to the MF, I think you mean magic formula, that is built right into Atoms Car. And if you have the student competition bundle, you would have access to the tire data fitting that Ani showed just now. I have another question. Prabhanjan Subaya asks, can you briefly explain requests? Is there a graphical way to list or see components and requests related to them?
Yes, so in Atoms, as mentioned before, once you go into the template builder and you start building your model, you're going to have here your request. So in general, Atoms will give you results of any type of force and moments. But if you want to build something specific, like the toe for the suspension, you will need to create a request. In this case, it's already made, and it's taking advantage of a subroutines. These are inbuilt modeling techniques inside Atoms. But you could, this doesn't mean that you cannot build your own. And there is different ways of doing them. So you can create them by type and markers. So basically what's happening between two components. Subroutines as the one I just showed you, and function expressions. You may have a displacement or a velocity between different components, and that's what you want to measure up. So you will define that here. You have clicking this button will open a function builder, and you can create different type of measures, displacement, accelerations, forces, and so on. Once you have those here, then you will define the result here and give the right unit if you want, which is what the guys did with the subroutine. So it's just ignoring what's happening here. They're just trying to get certain kinematics out of the wheels, and that's how they do it. So you will be able to create your own.
I think that about does it for today's webinar. Alexis and Ani, thank you for the presentation, and everyone, thank you for attending. I hope that you found it helpful. Have a great day. Bye.
Thank you. Bye-bye.
Everybody.